All right. So here we are, and I have gotten a new PC. So it looks like this. It's a laptop from System 76. I'm not sure I can recommend it yet. But it has some nice things. We have an NVIDIA graphics card and decent CPU, a lot of memory, a lot of hard disk space. So I think we can do some interesting things with this. But now to begin with, to test out the computer, I want to take a look at Mojo, which is this programming language that's supposed to be specifically targeted to machine learning, but my impression is that it's just generally if you want to write code that really takes advantage of all the processing power of your computer, then this is kind of like a language you want to take a look at. So my idea is that we go through one of these examples and kind of try to understand a little bit about the different moving parts. And yeah, let's see where that takes us. So it's just going to be a learning project, so I'm not going to make a repository, at least not to begin with, most likely. I already have Mojo installed, so we can just immediately do stuff like print the sum of some numbers, and we should be able to just run things. So let's make a file and let's try to I think we need a colon. Let's try to just run it. We don't need a semicolon, I bet, and we can go here and say did I make an oopsie? Anyway, so Mojo run, main Mojo, and another nice thing is that we can also build an executable. So now we have an executable and we can run it and it works. I just had a small hiccup with the Tmux configuration, but I think we should be good to go now. So let's keep trying. So now my Tmux should be working. All right. So we got a bunch of imports here. Benchmark, I don't know what that is. So should we look it up? Let's open up the docs and check the cookies. And it's not this one, maybe here. So how do we search it? Benchmark. And nothing comes up. Something did come up. So runtime benchmarking. And what's the point of this? I guess it's just a way to time things. It doesn't seem to be doing anything other than that. Okay, but that makes sense. Then there's some complex numbers, and you can do single instruction, multiple data stuff with that. IOTA, I guess we'll see with that. You can get the number of cores. And then these are very interesting. There's some automatic parallelization and vectorization of algorithms. We're going to have to take a look at how that works. Some tensors, so multidimensional arrays, and something called index. And what is index? It's with capital I, so let's try this one, and you have to close it. Constructs a 1D index. from the given value. Okay, so I don't know what that's all about, but I guess we will see. Let's copy paste this and put it up here. All right, anyway, so then there's some parameters that have to do with the Mandelbrot set. Those are not so interesting. Let's just copy paste those. And then what this example is calculating is this Mandelbrot set thing. So we'll make a picture like this, I think. And the way you do that is you kind of iterate this function many times, and you see whether the result goes up to infinity or it doesn't go up to infinity. So let's check this out. So here is something they call a kernel, which makes me think of GPU programming or something like that. But this is something that operates on a single complex number, which is usually associated with a single pixel and this kind of thing. And then it just iterates the function. And then we have this compute function, which constructs a tensor with a given float type. And it does it as a 2D array, so it's like an image. And then it just calculates minimum y and x. Okay, so it just loops over every pixel and calculates the number of iterations required to go up to infinity, or to like to go to escape, by iterations required to escape, and then stores them in this tensor and returns the tensor. So this is like probably the benchmark or like sequential single-threaded implementation of this algorithm that just runs on the CPU. Okay, so now this is kind of like a notebook. So here they're running some Python stuff. So I suppose we can also, because I don't think I have anything, so let's install these two. And that's not how you do it. You have to actually say install. So while that is running, we can keep looking. Then we shouldn't need this thing. And now an interesting thing about Mojo is that there's kind of two types of functions. There's def functions and fn functions. And def functions are more Python-like. And these are kind of like more C-like from what I have seen, but like I don't really know so much. Okay, so we have imported up here Python. So that means that we can use Python modules like this. And the Copilot is very confused, so I'm going to disable it. So we can import NumPy and we can import matplotlib and just use them. That's another thing. I mean, you can think what you want about Python, and I also have my reservations, but there's just so many useful things implemented in Python that it's hard to deny that you can get a lot of stuff done by using Python. So anyway, we make a NumPy array with the size of the screen that we want. So the idea is that we will calculate things using this this tensor type, this Mojo tensor type, and then we'll transfer it to this NumPy array probably. So then we have this thing. Again, we loop over Okay, so we actually, in this function, we already have the tensor. And here we are just setting the, maybe I should just have copied this, but sometimes it's nice to write it out. So here we just copy it directly. This stuff I don't want to write, so let's do this. Paste. And so this is very similar to Python code. It just sets up a plot, does something weird with light source. I've never done that before myself. But then it shows the image that we got as an input. So as I said, this is kind of like a notebook. So they just call show plot there. We cannot do that, so we have to kind of say do it here in the main function. Show plot and compute Mandelbrot. So let's first clear this and let's try Mojo run in.mojo. And it failed. And that is because it says try surrounding the call in a try block. So if we do this, I'm just gonna try to write it as if it were Python. And here it says unknown, which is and here I wrote wait. It should be width. Let's try to run that again. And that kind of seems to be working. So here we have computed a Mandelbrot 7 image. All right, so we can construct this image, and it was actually kind of fast. Well, how big is the image again? So pretty big, and calculated quite fast. So now we're gonna vectorize it. We showed a naive implementation, but there are two things we can do to speed up. We can early stop the loop iteration when a pixel is known to have escaped. I kind of thought we already did that. This thing. And we can leverage Mojo's access to the hardware by vectorizing the loop, computing multiple pixels simultaneously. To do that, we will use the vectorize higher order generator. We start by defining our main iteration loop in a vectorized fashion. So we cannot just use this. It seems like we cannot use this kernel. We're specifically making a different kernel for that. So that's interesting. And we have, or maybe I do something like this. So what do we have here? We have a couple of, I think these that are inside the square brackets are kind of like compile time arguments, and this is runtime argument. So it's taking a complex number similar to this one, but now in these vector types. So it has a certain type and it has a certain width, and it returns just a single number of a float type, not a complex number, and this width. So then we have, we just kind of directly write it with SIMD instructions, SIMD. SIMD maybe is how you're supposed to say it. And then there is this, this is just initializing things to be 0. And then here's the main loop. There's a T, which is kind of like some booleans. And here we say not, or, so that means that if all of them are false, Then we stop. And here we update t and we say, are they less than 4? So this one is kind of like, should we still keep iterating? So y squared, we just multiply them. That's kind of nice. You just use the multiplication operator. I think in C you would have to do something more verbose. And then y is fma. I think f is fast and m is multiply and a is add. Could that make sense? So this would be something like x multiplied by 2y plus cy. I think that's exactly what you want if you do multiplication by complex numbers. So, but we can check here. What is FMA on the SIMD? Oh, it's not fast, it's fused. Okay. And it is indeed the first thing multiplied by the second thing plus the third thing. All right. So fused multiply add. So I guess it's like one instruction or something. Then we have one instruction where we again do fused multiply add, and this thing is, maybe we can write it out. So this is 2xy plus cy, and this is x squared plus y squared. And here we're checking if it's less than 4. So this is if we should still keep iterating. And here we have x squared minus x minus y squared. And here we apply the select operator, and the select checks in each entry of this is it true or false, and if it's true it selects the first one, and if it's false it selects the second one. So update iter count if we are still iterating. Maybe I zoom in a bit. Maybe that's too much. Okay. Great. And the important thing about this is here we are operating on basically 4 numbers or something like that. I'm not sure what the width of my machine has. What did we set it to? 2 floats. Okay. So great. So here we have a function called vectorized. Let's go ahead and see what that does. And again, we have this call, random call there. Okay, so first it constructs a tensor, presumably of all zeros. Then there is this parameter thing. What is that? That didn't work. So it's a kind of a decorator. And it's a higher order function. Okay, it takes a function, returns a function that extend. Okay, it can extend the behavior of a struct as well, or some other code. Instead of actually calling the higher order function, you simply add the decorator. So this is very similar to Python decorators. And this one executes a function on if statement at compile time. So presumably it means that this code is, in Python, this would be kind of executed and a function would be created every time you call this function. So at runtime and every time you call it, but here it's just called once at compile time. So you could presumably write it outside the function, but then other functions could also use it. So it's kind of a way to namespace it in a way. I think. All right, so let's keep going. So this one is a worker function and it operates on a row. So it seems like we're going to be calculating each row of the image one at a time. This I'm not so interested in. Then there's something called copy capture. What is that? That doesn't say here. Maybe it says here what it is. No, it doesn't explain it. Okay, whatever. And we didn't get an answer over here either. This is a little bit disappointing. So I guess we'll have to guess what it does. So capture is probably that these parameters that are defined here, they are captured. So they are kind of, there's a local copy inside the function and they are copied. So it's not a reference, it's just straight up copy. Then there's this parameter. So this is also only executed once at compile time and at compile time. And it computes a vector for a certain column. And it also has this with how many numbers we operate on parallel. Each time we operate on, so let's say two pixels. And what is iota? I think I know what it is, but let's see what it is here. So iota okay, I didn't know what it is. Creates a SIMD vector containing an increasing sequence starting from 0. Okay. So we have X, we have the column, and then we have like 0, 1, 2, 3, 4, however many numbers we decide to operate on in parallel. So it will take like some columns side by side, and it's scaled, and there's just one Y. And then we put that into a complex SIMD number. And then we have T. And what is T? T is the tensor. We access the data and we store, I suppose, at this location, we store the result of calculating this number in parallel. Okay. And here is a function called vectorize. That is very interesting because I think that is like a built-in vectorization. Simplify SIMD optimized loop by mapping a function across a range from 0 to size, incrementing by SIMD width at each step. Okay. So the way I'm understanding it is that it will call this function on every number from 0 to width, but in steps of whatever number this is. So we can actually check that. Let's try to test that. So let's have just like print number, and this can be SIMD width, and this can be 10. Let's make print number, and up here we saw that the input has to be an integer. And it's capital in this language, yes. And we're just gonna print it. So let's comment this out. Okay, I need to update my thing, and let's try to run it. And candidate not viable. Interesting. Interesting. So it means that this one has to have, I think, this. Let's run it again. It still didn't work. Okay, still some issue with my Tmux setup, but I'm not going to worry about that right now. Okay, so what happens when I type run? Okay, no matching function in call to vectorize. Candidate not viable, call parameter 0 has but value has type. Okay, I don't understand what's going on. I'm just going to try some stuff until it gets boring. So I don't know why, but for some reason that worked. Okay, so this is just kind of a pattern I guess I have to learn. So what happened? It only printed 3 things. And what is SIMD with? That's also interesting to know. Just making sure. It's 8. Okay, that's okay. Great. So then it makes sense. Then it makes sense. It's in steps of 8, and that's why we only got 0 and 8, and then also 9, which is nice that it also includes the very last one. Okay, so that makes sense. So this vectorize is a way to call a function multiple times. It's basically equivalent to print number 0 and then print number 0 plus whatever this number is, and then it will keep doing that until it reaches whatever this is. Okay, so in our case it will be 0, and then it will be so it will be 0, then it will be 8, and then here it will be, you can even, it should be times 2, and then probably 10 minus 1 or something like that. Anyway, so here's 9, so it also gets the last bit. All right, back to understanding the function. So here in this vectorized, we make the image, we make this helper function worker, which for a given row, it calculates all the pixels in that row, and it does it 8 pixels at a time for this particular machine. And then we have this benchmark function. Okay, it just calls one after the other the worker function on each row, so it calculates each row one at a time. And then we make a benchmark run on this function. Max runtime is 1/2 second, and we present the average time in milliseconds. Okay, can we just try to call that? So vectorized and run, it's like that. And here we are. So it took 12 . 12 . 12 . 12 . 12 . 12 . 12 . 12 . 12 . 12 . 12 . 12 . 12 . 12 . 12 . 12 . 12 . 12 . 12 . 12 . 12 . 12 . 12 . 12 . 12 . 12 . 12 . 12 . 12 . 12 . 12 . 12 . 12 . 12 . 12 . 12 . 12 . 12 . 12 . 12 . 12 . 12 . 12 . 12 . 12 . 12 . 12 . 12 . 12 . 12 . 12 . 12 . 12 . 12 . 12 . 12 . 12 . 12 . 12 . 12 . 12 . 12 . 12 . 12 . 12 . 12 . 12 . 12 . 12 . 12 . 12 . 12 . 12 . 12 . 12 . 12 . 12 . 12 . 12 . 12 . 12 . 12 . 12 . 12 . 12 . 12 . 12 . 12 . 12 . 12 . 12 . 12 . 12 . 12 . 12 . 12 . 12 milliseconds to run this function, I guess. So it kind of means that what if we get rid of this? Okay, give me a second. All right, I just updated my new Vim configuration just so it knows about Mojo files, so we can easily comment things. So now we call this function, and then this should basically be instant, I would guess. So we can even try to build it first. Okay, and then we can try to run it, and it's segfaulted. So that's great. We can try to run it like this. It takes a while. It's not 12 milliseconds, but what if we print something here? So that's quite fast. But let's go back to this original code. Okay, so this is interesting that it doesn't just work out of the box with build, but this is not something I want to fix right now. Okay, so this is calculating each a bunch of pixels in parallel using like intrinsic parallel operations that the CPU has. But it's only using one core still, if I'm understanding correctly. So we can try to do this. Use this parallelize function, which I assume will also use multithreading. So again, we make a tensor. Compile time, we make this function. Great, so we still use SIMD operations for each row. But now here we go. We use this parallelize thing, which I'm going to, it has two heights, which is interesting. I guess this, like, one is the maximum number of threads, most likely. So let's have a look at that. So parallelize, and I guess it's this one we're calling because we have two input arguments. And again, there's some compile time things, function, capturing none. Is not entirely sure what that means, but that's all right. And I suppose this is like, it has to take an integer as the first argument, and then it can have some other things. But anyway, so it executes this many things in parallel, and this is the number of workers to use. So then there's a benchmark again, and we can try to, even try to run both of them. So parallelized. So this is a thing that's kind of cool. It's relatively easy to write parallel code. We'll get rid of that. And now we see there's kind of a factor of 12 speed up, which is super cool. We almost didn't do anything. In fact, if we look at the difference between the two, it's the only thing we changed is that this function, instead of looping, it just has this parallelize. There's kind of a built-in parallel loop in this language, which is cool. Here we increase the size to something, and this one I'm not so interested in because we already know it's pretty great. So what is the number of threads? Number of physical cores. We can try to print that. So let's comment that out and print number of physical cores. That seems to be a function. Okay, that's fine. 24. Great. But yeah, I think that's it for this video. So Mojo seems really interesting in that it's super easy to write SMD stuff. At least in C, I think it's very complicated, or like it's not complicated, but it's not more complicated than this, but it's quite verbose. And here it's kind of like almost natural. But then there are these automatic ways, convenience functions. I mean, it's not much more than something like this, I guess. And this is just simply width, and then we would give the column here. It's almost like this, or if we have a C style loop, it would be this basically. Yeah, so the column is less than the width, we loop from 0 to width, and each time we step by this much. That's what this function does. I mean, I'm sure it does something more smarter than that. Maybe it unrolls it or whatever, but conceptually that's what it does. All right, but I think, yeah, I think that's gonna be it. And I think we're gonna look a little bit more at Mojo. Maybe we'll look at this ray tracing. Maybe we'll look to see if we can get Raylib to work. And yeah, that's it. And until next time, bye bye.